If u and v are two differentiable functions of x, the derivative of their product uv is u prime v plus uv prime. This means the product uv is an antiderivative of u prime v plus uv prime. Here is the symbolic representation of this relationship, where c is the constant of integration. Now, we split the integral as a sum of two integrals. And subtract the first integral from both sides. Since the right-hand side also includes an indefinite integral, we can omit the constant c. This is called the formula for integration by parts. It splits the integral of the product uv prime into two parts. The formula for integration by parts is often written in terms of differentials du and dv. In the formula, d prime dx can be replaced with dv, the differential of v. Similarly, u prime dx can be replaced with du, the differential of u. However, in this video, we will use the first version of the formula. To simplify the use of this formula, we present it in a tabular form. The integrand on the left is the product of u and v prime. The right-hand side of the formula includes u prime and v. So, we differentiate u to get u prime, and integrate v prime to get v. To indicate the operation in each column, we label the first column with d for differentiation, and the second column with I for integration. Now, let's track each part of the formula using the table. The first part, uv, is the product of the terms connected by the solid arrow. The second part is the integral of the product of the terms connected by the dashed arrow. Let's place the sign of each part just above the corresponding arrow. Thus, the table captures the process of integration by parts for the product of u and v prime. The integral indicated by the dashed arrow may require another round of integration by parts. In that case, we simply extend the table by adding another row. Since the integral of u prime v already carries a minus sign, the first part and its antiderivative will be assigned a minus, and the second part will be assigned a plus. These two parts replace the integral of u prime v. This process can be continued as necessary by repeatedly differentiating the functions in the first column, integrating the functions in the second column, and alternately assigning plus and minus signs to the terms indicated by the arrows. Observe that the only integral requiring evaluation is the one indicated by the dashed arrow. This term can be disregarded when the corresponding function in the first column is 0. Now, let's walk through some examples to clarify the tabular approach to integration by parts. We'll start by integrating the product, x times cosine of x. Use x as u, and place it in the first column for differentiation. Use cosine of x as v prime and place it in the second column for integration. The derivative of x is 1. And an antiderivative of cosine of x is sine of x. The two parts of the integral are indicated by the arrows, with alternating signs, plus for the first part, and minus for the second. For the first part of the integral, we just multiply the terms connected by the solid arrow. So, the first part is x times sine of x. For the second part, we multiply the terms connected by the dashed arrow, including the minus sign, and integrate. This is the second part of the integral. Now, we integrate the second part. Add c as a constant of integration, and simplify the expression to get the final result. In fact, we could have completed the entire integration directly within the table by performing another round of integration by parts. This is the kind of situation where the tabular method proves highly efficient. As before, the first solid arrow gives the first term of the antiderivative. we multiply the terms connected by the second solid arrow, including the minus sign, to get the second term of the antiderivative. The term corresponding to the dashed arrow is omitted, since the product of the corresponding functions is 0. Finally, we add the constant of integration, c, to complete the integration process. Note that, if we switch the roles of x and cosine of x in the previous example, the integration by parts will not be helpful. The integral on the right is even more complicated than the original. Thus, placing x in the second column does not work in this case. Is there a universal rule for choosing the function u or v prime? Unfortunately, no. However, the mnemonic, Lie8, often provides a helpful guideline for choosing the function, u. It stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential functions in that order of preference for the function u. Note that, we must be able to integrate the function placed in the column I. Still, in some cases, trial and error is the only way to determine what works. Now, let's integrate x cubed times e to the negative x. Using the Lie8 rule, we place the algebraic function x cubed in the first column, and the exponential function e to the negative x in the second column. Note that x cubed becomes 0 after differentiating 4 times. And we can integrate e to the negative x as many times as needed. So, we will go through 4 rounds of integration by parts, differentiating x cubed 4 times. And integrating e to the negative x 4 times. The 4 terms of the antiderivative are indicated by the solid arrows, with plus and minus signs assigned alternately. The product of the functions connected by the dashed arrow is 0. So, we ignore the integral it represents. Finally, we write the sum of the products represented by the solid arrows. Add the constant of integration, c, and simplify. Now, let's look at an example where we use integration by parts, even when we're integrating just a single function. To integrate the natural logarithm of x, we rewrite ln of x as ln of x times 1. Place ln of x in the first column, and 1 in the second column. The derivative of ln of x is 1 over x, and an antiderivative of 1 is x. The 2 parts of the integral are indicated by the arrows, with alternating signs, plus for the first part, and minus for the second. For the first part of the integral, we just multiply the terms connected by the solid arrow. So, the first part is x times ln of x. For the second part, we multiply the terms connected by the dashed arrow, including the minus sign, and integrate. This is the second part of the antiderivative. Finally, we integrate the second part and add c as a constant of integration. Now, we discuss an interesting example of a boomerang integral, an integral that comes back around. To integrate e to the 2x times sine of x, place e to the 2x in the first column, and sine of x in the second column. The derivative of e to the 2x is 2 times e to the 2x. And an antiderivative of sine of x is negative cosine of x. The 2 parts of the antiderivative are indicated by the arrows, with alternating signs, plus for the first part, and minus for the second. Let's look at the second part, which is obtained by multiplying the terms connected by the dashed arrow, and then integrating. This integral isn't any easier than the original. So, the integration by parts doesn't seem helpful, at least not yet. Let's see what happens if we perform another round of integration by parts. Now, let's write out the terms indicated by each arrow. Wait a minute, this is exactly the original integral. So, did we really do all that work for nothing? Not quite. Getting the original integral back is actually a good sign. Denoting the original integral by script I. We now have an equation that we can solve to find the given integral. Adding 4i to both sides, we find the expression for 5i. And include c0 as the constant of integration. Now, we multiply both sides by 1 over 5 to solve for I. Finally, we simplify the expression and denote 1/5 of c0 by c.